Okay, so last class we talked about moles and that they are like a conversion factor or a uh, kind of like a dozen, right? And so this chart kind of helps you break down all the different conversions we can do with moles. So the first part I wanted to look at are the grams of the element. If you have grams of the element, or grams of a compound, doesn't matter, either one. If I give you grams or give you mass, then you're going to want to use the molar mass. You're going to want to use the molar mass, which is how many grams per mole. So you'll get this number of grams. So the molar mass is 1 mole of something is equal to the number of grams of that thing. You get this number from the periodic table of the elements, and you add up every element in that compound if you've got a compound. The next part is the moles of the element, or the moles of the compound. So if I give you moles and ask you for grams, then you know to use the molar mass. If I give you mass, ask you for moles, use the molar mass. What if I give you grams and ask you for atoms or ions or molecules? Then you'll come over here and you'll be using Avogadro's number. And so Avogadro's number is 1 mole of something is equal to 6.022 times 10 to the 23 particles of that thing. And your particles can be atoms, ions, molecules, or if you're dealing with an ionic compound, your particles can be formula units. Any little tiny thing that we're talking about, you can use Avogadro's number to kind of go to a large number of those little things. What we didn't talk about in class, we're going to talk about now, are how do you go from moles of one thing to moles of something else. And so we're going to be using subscripts, and we're going to be using balanced chemical equations to do this. So we're going to get a little more in depth into using moles. And so the first thing I want to look at is how a chemical formula is actually a conversion factor. And so if we're looking at this 3-leaf clover, if I say 1 clover has 3 leaves, then you can turn that into a conversion factor. You can say 3 leaves are equal to a clover, and then if you have 14 clovers, how many leaves do you have? Well, you just set yourself up with a conversion. It all has to do with a ratio. So a ratio you can set as an equality. So think about those two lines as you can set as an equality. And then if you've got an equality, then you can set it up with dimensional analysis. So chemical formulas are the same way. And so if we look here at this water molecule, in one water molecule, there are 2 hydrogens, right? And so I can set that as an equality since it is a ratio. I can also say 1 oxygen atom is equal to 2 hydrogen atoms if I'm talking about water. Or I can say 1 oxygen atom is equal to 1 water molecule. Because they have the same ratio, I can set them as an equality. So go ahead and pause and see if you can figure out the number of moles of oxygen and 1.7 moles of calcium carbonate. Okay, so for 1.7 moles of calcium carbonate, how many oxygens do I have in calcium carbonate? 3. So in 1 mole of calcium carbonate, and I can use mole and molecule, or I can use atoms, but moles are just a generally better unit for me because it's like a bundle of those small things. So it's a 3-to-1 ratio. So there's my conversion. So I'll set this up, and I'm going to say 1 mole of calcium carbonate is equal to 3 moles of oxygen. Can you also say 1 formula unit of calcium carbonate is equal to 3 atoms of oxygen? Sure. But because formula units and atoms all go by Avogadro's number, we can really just simplify it all to mole. So these are, I'm going to call these things mole ratios. That's what I'm going to call this mole to mole thing that we're doing here. Okay, let's do another one. Pause and see if you can figure out this question. Okay, so if I'm giving you mass of sodium, so I want mass of sodium, so let's go to grams of sodium, and I give you grams of sodium chloride. So I'm going to need molar masses, right, because I give grams. So 1 mole of sodium is equal to 22.99 grams of sodium. I get that from the periodic table. 1 mole of sodium chloride is equal to 58.44 grams of sodium chloride. This is me adding up sodium and chlorine. Now, if I'm looking at like my conversions here and seeing do I have everything, so I have grams of sodium to mole of sodium, and then I don't have mole of sodium, so I need to write another conversion. Well, in 1 mole of sodium chloride, how many moles of sodium are there? Right, there's 1 mole of sodium. So here's my mole ratio. So now I can go from grams of sodium, moles of sodium, moles of sodium, moles of sodium chloride, moles of sodium chloride, grams of sodium chloride, to back to where I want. And so let's set this up. Sorry, 15, nope. Grams of sodium chloride. So the first thing we need to do is get rid of the grams by dividing by the molar mass. And that's equal to 1 mole. Then 1 mole of sodium chloride is equal to 1 mole of sodium. Now this isn't always going to be a 1-to-1 ratio, so make sure you're familiar with the concept. So first we're going to use our molar mass. Then we're going to use a mole ratio. Anytime you have to change substances, you should be using a mole ratio. And then 1 mole of sodium is equal to 22.99 grams of sodium. This is another molar mass. This is going to be a big pattern for us. Molar mass, mole ratio, molar mass. And then let me do a quick calculation. And we should get 5.9 grams of sodium in that much sodium chloride. So it's kind of like using the subscripts as conversion factors. And so here's another example. If you have carbon tetrachloride, you've got 4 moles of chlorine. So we're going to put all this together into something called stoichiometry. So stoichiometry is the numerical relationship between chemical quantities in a balanced chemical equation. So here you have to make sure that we have a balanced chemical equation to do this. We can just pretty much predict how much reactant, how much product, what we should expect from any reaction. And so to kind of simplify this concept, we're going to look not at chemistry first, but at cooking. And so let's say I'm trying to make some pancakes. My recipe is here, and this relationship, this ratio between ingredients, well, that is just stoichiometry. And so if I want to make 5 pancakes, I've got to put in a cup of flour, 2 eggs, and a half a teaspoon of baking powder according to this recipe, which is just like, if you kind of look up here, kind of like a chemical equation. And so let's look at some math. If I have 8 eggs and 2 eggs make 5 pancakes, how many pancakes can I make if I have plenty of everything else? If I have 8 eggs. Right, so if I have 8 eggs, I can make 20 pancakes. Well, here's a conversion. This conversion is just the ratio that I saw in my recipe, which is the same thing as my chemical reaction. And so we're going to be using this ratio to help us with chemical reactions. And we call this a multimole ratio. Again, the same kind of thing, it's just that instead of just looking at the subscripts, we're looking at the whole chemical reaction. So let's look at this reaction. This reaction is hydrogen plus nitrogen makes ammonia. And when we balance it, we get 3 hydrogen molecules, 1 nitrogen molecule, and 2 ammonia molecules. To do a multimole conversion here, we have to come up with our conversion factors. So, because these are all small particles, right, it's not really helpful for us to use these as a ratio, because when we're dealing with such small things, a mole or a package of them is a better idea. So actually, it's the same conversion factor for all of these, and so they're still going to it's remaining the same ratio because we're just dividing by Avogadro's number for all three of them, so it keeps the same ratio. So we can just call this a mole ratio. These numbers here correspond to the numbers in front. So nothing in front means 1, 2 in front means 2, and then the unit for these numbers is just going to be moles. So instead of baking and units are cups or teaspoons, the unit here for reactions, we're just going to assume we're talking about moles. So here's an example. Oops. It didn't say very well. So at the very bottom of the screen here, there's an example. So go ahead and pause and see if you can figure this one out. So if we have 3 moles of N2 and more than enough H2, how much NH3 can we make? Alright, so we're looking at this problem on the very bottom because I messed up with the presentation and it's got the answer down there. Okay, so if we have 3 moles of N2 and more than enough hydrogen, okay, so don't worry about the hydrogen, how much ammonia can I make? Well, let's look at how much, so let's just look at moles of ammonia, because mole is a measurement of how much. I need a relationship between nitrogen and ammonia. So I look at my chemical reaction, I see that there's a 1 here and there's a 2 here. So 1 mole of nitrogen is equal to 2 moles of ammonia. That comes from my balanced chemical reaction. And so I can set this up as 3 moles of nitrogen in a 2-to-1 ratio will give me 6 moles of ammonia. So if we're going to kind of continue this, we can think about using the mole ratio as a middle ground, right? Like we did with the sodium chloride before. So in the middle, we're going to be using the mole ratio, and we can use molar mass on either side. So this is going to be called a mass-to-mass conversion, which is a very typical conversion you're going to use in stoichiometry, especially in study assignment 12. And so, I did the same thing. Alright, so looking at this question down here, what mass of carbon dioxide is emitted by an automobile per 500 grams of octane? So this is octane. So go ahead and see if you can figure out, first start with just the molar masses if you need to, and then see if you can kind of figure out how to work this out. Okay, so to work this out, we're going to find the molar masses first because I'm given mass of octane. So I need the molar masses. So to find the molar masses, I'm going to do 8 carbons. I'm going to do 18 hydrogens. And I'm going to add that up. Don't put anything regarding the 2 in your molar mass because molar mass by definition is only for 1 mole. And so don't worry about the fact that there's a 2 in front. I get 114.26 grams per mole, and this is of octane. So I need to make sure I'm writing what it's for. Okay, and then they ask me what mass of carbon dioxide, so I can really honestly ignore everything else and just do carbon dioxide. So now let's look at carbon dioxide molar mass. Oops, I have 1 carbon and I have 2 oxygens. Ignore the 16. That 16 does not influence the molar mass. Wow. 44.01 grams of CO2 is equal to 1 mole of CO2. And so now I have this conversion from grams of octane to moles of octane, but I don't have a conversion between moles of one thing and moles of another. Well, I do have a conversion. So here's the conversion. 2 mole of octane is equal to 16 mole of carbon dioxide. And I get these numbers from my balanced coefficients. So now we can kind of finish our little map here. So I have grams of octane to moles of octane to moles of carbon dioxide to grams of carbon dioxide, and that's what I want. Right, so I have all my conversions. So let's see what it looks like all done. So, sorry, there's a lot of numbers here. I want you just to focus on this line right here. Okay, so this is your line of work here. So you see that we're doing the same thing kind of over and over again, using the same conversions just in different orders or different ways depending on what we want. And that's kind of the whole point of chemistry, is like just getting what you want with what you have and creating what you need from this problem or from this reaction or from this anything, right? And that's the kind of the basis of chemistry and solving those problems. And so what I want you to do now is I want you to really work through study assignments. Let's see, you can do 9 is balancing, 10 is writing equations and balancing, 11 is mole conversions, and 12 is stoichiometry, which is just this mass to mass conversion. If you want to try to move forward, you can watch videos. I think there's some videos on limiting reactants in Canvas, but I'm not going to require you to do that until we get back to class together on Thursday. So there will be no limiting reactant on the quiz. It'll only be up to what we just did right here in this video. Okay? All right. I hope that you have a good Tuesday, and I will see you guys on Thursday, including your for your quiz in Chapter 7. Everything except everything up to limiting reactant, so no limiting reactant for that, okay? All right.